Hello engineers, welcome back. In this video, we're going to start a new data structure called queues. I hope you're ready. Let's get started. So in this video, we're going to look at what queues are. We'll look at some real world examples of queues. We'll discuss the structure of a queue. We'll try to code all these operations in C++ using linked lists. And then we'll discuss the time complexity of each operation, right? Let's get started. So what are queues? So a queue is another linear data structure that follows the concept of FIFO. FIFO stands for first in, first out. Okay, so whatever goes in first will come out first. In stacks, we have seen that whatever went in first came out last, but in queues, whatever that goes in first will come out first. Okay, so what are some examples of queues? In the software world, we commonly see the usage of queues in printers. So whenever we try to print a bunch of things, one document gets printed at a time, right? And then the next, and then the next. So they are put in a queue and then processed one at a time. So this is a very good example of a queue. Another example can be our video streaming, right? Let's say YouTube or Netflix. So whenever we are trying to watch a long video, we see that a small portion of the video is buffered first, and then the next portion is buffered, and then the next portion. So this is called a buffer queue. So small segments of the videos are being pushed to the client, and then we can see those videos without any interruption. Third example can be seen in microservices when we use queues like RabbitMQ, right? So when two microservices are trying to communicate with each other, one service will put a message in the queue and another service will consume it. So if the service is putting multiple messages inside the queue, they will all be added in the queue and the consumer service will process one at a time. So this is another very good example of a queue. Okay? So queues are quite useful while building some complex applications. Okay. So now let's discuss the structure of a queue. So how does a queue look like? Okay, let's say there are three elements in my queue, 10, 20, and 30. As we know, 10 is the first element and 30 is the last element. So the first element is called front and the last element is called rear. We can also call it back, right? So these are my pointers. So we're going to use linked lists for our learning of queues. But since this is a linear data structure, the same can be implemented using vectors or arrays in the same way. Okay. So this is how the structure of a queue looks like. There is a front element, then there is a rear element, and then in between are the remaining elements of the queue. Okay. And when we want to add any new element to the queue, we add it at the rear. So if we want to add 40, we create a new node called 40. We point the rear element to the new node like this. And then we move the rear pointer backward. Okay. So when we are adding elements to the queue, the elements are getting added to the back. But when we are removing elements from the queue, they get removed from the front. So first we move the front pointer forward. And then we remove the connection and we delete the front element. Okay. This process is called dequeuing. When we are adding the element to the rear, it was called enqueuing. Now this process is called dequeuing. So that's all there is to queues, right? When we want to add an element to the queue, we add it to the back of the queue. When we want to remove element from the queue, we remove it from the front. So that is how queues operate. Okay. Now let's see how we can code all this in C++. So as we are trying to build it with linked lists, let's see the structure, how it will look like. So every element is a node, right? And every element will have two things. One is the value and other is next, right? And the next will point to another node like this. That node will have another value and another next, right? So every element is a node and the queue will have two pointers, front and rear. Okay. Front will be at the first element of the queue, rear will be at the lastmost element of the queue. So let's see how we can do this. So I've created a new folder called queues. I've created the base template so we can get started. So for making queues, we will need two things. First is the node. Okay, so let's templatize it so that we don't have to build for every data type. Okay, now what do we need? Like I said, every node will require value and next pointer, right? So let's make everything public and we can call it t value. We don't know the data type, we'll call it t. And then we will need next pointer. Okay, and then we'll have a constructor. Constructor will take in a value of type t and it will just initialize. So this arrow value will be value, and then this arrow next will be null ptr. Okay, so whenever somebody is calling the node, whenever somebody is trying to create a new node, they will get a node with a value, given value, and next pointer being null. Okay, next, what do we need to build the actual queue? So we will need queue, and this will be also templatized. And it will have two private things. One is a node pointer called front. Another is a node pointer called rear. Okay, so since we are using templates, let's put t everywhere and done. We also need another variable for size. Okay, so that we don't have to recalculate size every time, we can just use this. Now let's build the constructor. Constructor will not take in anything, it will just initialize everything. So this arrow front will be null ptr. This arrow back or rear will be null ptr, and then this arrow size will be 0. Okay, so this is our initial state. We have one front, one rear, and size is 0. So let's parallelly build this. So we have a front which is pointing to nothing. We have a rear which is also pointing to nothing. And let's put size somewhere else. Size is okay. Now let's build our first operation, enqueue. Let's see what do we need to do enqueue. Now our queue is empty, right? There is nothing in the queue. So when we want to build our first node, what do we need? So first we need to create a new node, right? Let's create a new node. Let's call it 10, the value 10, and the pointer is next, null, sorry. Next pointer is null. Now because our queue is empty, we need to point the front pointer to this and also the rear pointer, because there is only one element, that is the front of the queue, and also the rear of the queue, right? So let's just point it here. So front and rear are pointing to this guy. Okay. But when we want to add another node, this time the queue is not empty. So what do we do then? We create a new node that is pointing to null. And now what do we need to do? We need to change the rear pointer, right? Rear should go to 20 now. So our enqueue steps are, so what do we need to do here? We need to change this pointer to 20. So this is what? Rear arrow next, right? So what we can do is rear arrow next will become new node. So this connection is now established. This is not null, but now this is established. And we are not done. We need to move rare pointer to this guy. So rare also will become new node, right? Now rare is here. Okay, so that is our enqueue process. And of course, we will parallelly increment the size. Now size is 2. Okay. So when there is an empty queue, we will add a node and make both front and rear to the same node. But when the queue is not empty, we will add a node and move rear pointer to that node. Okay. So let's build our function. Void enqueue. This will take in a value. Now let's create a new node. Node star new node equals new node star. Again, template. New node of value, whatever value we got from there. Okay. Now a new node is created. Now we need to make the connections. So first we check if front equal to null ptr, then both front and rear will become new node, right? And size plus plus, and what else? And nothing else. Return. This is the case of empty queue. But when the queue is not empty, we have the new node. We need to point the rear to this. So rear arrow next equals new node, and rear also will now be new node, and again size plus plus, return. Okay, so when there is an empty queue, we've made both front and rear to the new node size plus plus. When queue is not empty, we have made the next pointer of rear to the new node and then move the red pointer forward and size plus plus. So that is enqueue. Now let's look at dequeue. Now let's say we want to remove this element. Sorry, removing is from front always in the queue. Dequeue is always from the front. So if front is empty, nothing to remove. So we will simply say queue is empty. But when the queue is not empty, we need to check. Let's see what we need to do here. So now this connection is no longer required and front needs to move forward. So these are the two things we need to do. Front needs to move forward and then we can remove this. So front equal to front arrow next. So front is move forward, and then we need to remove this element, right? So before we move the front forward, we need to capture it. So let's capture it. Temp equal to front. Okay, we have captured the front in some temp pointer, and then we move the front forward. Now we can remove this connection. So we can say temp arrow next equal to null, and then delete temp. Okay, so first step is make a new pointer called temp. So let's create a new pointer, temp. Temp is pointing here, and then we moved front pointer forward. Front was here, now front is here along with rear. Okay, and now temp arrow next equal to null, so this is removed. Next, delete temp, this is gone. Okay, and because temp is a temporary variable, even this is gone. So now our front and rear are pointing to 20 and we are good. Okay, now let's see here. If I want to dequeue from this state, now front and rear are both pointing to 20, right? Right? Both front and rear are pointing to 20. Now if I remove this one, let's see what happens. Temp equal to front, so we get a new temp that is pointing to 20. and then front equal to front arrow next, which means front has moved forward, which means front is now pointing to null, and then temp arrow next equal to null, which is already the case, and then we delete temp, so temp is removed. Now front is pointing to null, but rear should also be pointing to null. So just as a best practice, we will make rear pointer also point to null. Okay, so that is our dequeue logic. So first dequeue. So first we check if queue is empty, which means if front equal to null ptr, we simply say cout queue is empty and return. But if queue is not empty, we make a new pointer called temp, and that will be front. Now front can move forward, and connection can be broken, and now it can be removed. Delete temp, right? And just as a best practice, if front has now become null, which means we have removed the last element, then rear also should point to null. It's just a best practice. Okay, and of course we need to do size minus minus, because we have removed one element from the queue, so size is now back to 0. Okay. So that is our dequeue logic. Now the remaining steps are simple. Let's see. Peak. Peak is, we are asking what is at the front of the queue. So void peak. If again, if queue is empty, we'll simply say queue is empty, nothing to do. But if the queue is not empty, we simply give the value that is at the front pointer. So cout front element is front arrow value and return. Simple. Next, display. Display is going through each node and printing the value. So void display. Again, if queue is empty, nothing to do. Now we can create a temporary pointer, use it to iterate over the queue and print each element. So node e star temp equal to front, and while temp not equal to null, we print each element, temp arrow value, and we move temp forward. Temp equal to temp arrow next. Okay, so temp will keep moving forward and we print each element, and that's it. Let's do a cout at the end of the print. Endl. Okay, so we are going through each node in the queue, printing the value, moving forward, and that's it. What else? Next is empty. Is empty. This will return a boolean. Is empty. So what is the check? If front is null, which means there is no element in the queue, we can simply return queue. We can simply return true, else return false. Okay. So this is the empty check. Next, get size. Size is again simple because we have used a size variable in our queue class. Void get size. This will simply print out the size of the queue is this arrow size. So if there is empty, it will become 0. Otherwise, it will give the size of the queue. Next, destructor. Very important, destructor. So what will the destructor do? It will remove all elements, right? So what is the process of removing an element from the queue? It is called dequeuing, right? We already have a function for dequeuing. We can directly use that. So let's build our destructor. So this is our destructor. We can do a statement saying destructor called. And how do we remove each element? We can check whether the queue is not empty, and when it is not empty, we remove one element at a time. So while is not empty, while queue is not empty, oops, while queue is not empty, you simply dequeue, and dequeue will do the remaining stuff. Dequeuing is what? Removing one element at a time from front, right? It will take care of removing connections, moving front pointer forward, making it null and things like that. So we don't need to repeat that logic again in destructor, right? We can simply call dequeue and it will take care of removing the elements. And inside dequeue, we have this delete temp anyway. So every element is removed from heap memory. And that's it. So let's see how we can use this queue. We simply say queue, and because we have used templates, let's give a data type called. So we have a queue available in main function right now. So let's add some elements to the queue. Queue.enqueue, let's say 10. And then after adding every element, let's do a display. Queue.display. Let's repeat this process for 20 and then 30. And then let's do a peak. And then what do we need? We need, let's dequeue everything now. Queue.dequeue. Before dequeuing, let's get the size as well. Queue.get size. And then let's do dequeue and display. Dequeue display. Let's do it 3 times. Okay. And then what else? I think that's good enough. After we do all this, it comes out of the main block execution and destructor will automatically get called. And we can see that. So no problem. So let's discuss what is the output that we need to see. First, when we do enqueue, we want our queue to be like this. 10 and 10 is pointing to nothing. So let's create this arrow for our visualization purpose in display. Okay, good. So we have added 10 here and the display will give us this. And we have added 20, so the display will now give us this with 20. We have added 30, now the display should give us 10, 20, 30 and okay. Peak will give us 10 because peaking is from the front of the queue. Next, size is 3 here. Next, dequeue and display. Now display will become like this. 10 will be removed and we will be left with 20 and 30. And we dequeue again. This time only 30 will be remaining. And we display again. We should see queue is empty. Okay. And let's add one more element for checking our destructor as well. Let's say we have added 40 and let's do display and we'll leave it at that. So our queue is now like this. There's only one element at the end, and destructor will take care of removing this. Okay, let's see. Okay, now we have the output. Let's compare. So we said first will be 10, and then 10 comma 20, and then 10 20 30, and then we did a peak. We got front element is 10, size of the queue is 3, and then we did dequeue. Now it became 20 30. Then we did dequeue again 30, and then we did dequeue again. Now we got queue is empty. Perfect. And then we enqueued something called 40. Now queue is 40, and then destructor is called, which takes care of everything. Okay, perfect. So that is our queue implementation using linked lists in C++. Now let's discuss the time complexities. Let's see. Enqueue. Enqueue is O of 1 because what are we doing? So what are we doing? We are just moving the rear pointer forward to the new node. So this is O of 1 operation. Dequeue is also O of 1 because we are just moving the front pointer forward and deleting the node. Peak is also O of 1. We are just returning what is available in the front. Display is O of n. We are iterating over each node and printing the value. Is empty is O of 1. We are just checking if the front pointer is empty or not. Get size is O of 1. Destructor is O of n. Okay. So this is how we can implement queues in C++. So if you have any questions, definitely ask me. That is it for this video, guys. Thank you so much for watching. Don't forget to leave a like if you found this helpful. Don't forget to bookmark the playlist. Don't forget to subscribe to the channel, share it with your friends. Thank you so much for watching, guys. I will see you in the next one. Cheers.